Alrighty, so now we are re-entering the realm of matched pairs. Now remember from experimental design that we were looking at three types of designs. We were looking at the completely randomized design. We also looked at a randomized block design, and then we looked at a matched pairs design. Now when using a matched pairs design, we had the following. We have blocks of size 2, and we have either matched people as similarly as possible. We've matched spouses or partners, and we've matched twins or siblings. Now, this could also happen where data is paired within the same experimental unit, such as in before and after studies, or where one person receives 2 treatments and we randomly assign the order. Now, matched pairs is a type of comparative study, and this is because we are either doing 2 observations on one individual or 1 observation on 2 individuals, and as you've seen from some of the examples, because 2 and 2. So maybe you have 2 individuals and they get 2 separate treatments, but the idea here is that we are still comparing. So maybe in a set of twins, we look at giving one genetically modified corn and one the regular corn. Or we look at 2 students with similar academic levels and one of them stands and the other sits. And again, we do this to try and minimize the variation in the treatments and the responses by the experimental units. Now, comparative studies also tend to be more convincing than single sample investigations. And that's just because, again, we're looking at the differences. We don't necessarily want to see what happened one time, but we want to see over the course of time what those notable changes are. Now, comparative inference is less common than single sample. That should have been flipped. My apologies, y'all. Give me one moment. As you can see, I just caught that. So it's actually single sample inference is less common than comparative inference. The reason being is that, again, one time, one sample doesn't really mean much, but comparing different populations or the population mean difference gives me a little bit more of an understanding. And we do so by measuring the same response variable twice, and we can compare and make comparisons by analyzing the differences in each pair. And we analyze pair data by first taking the difference within each pair to produce a single sample of the differences. So whether I'm doing before or after or treatment 1 and treatment 2, I'm going to look at the difference between the two. And from there, I'm just going to look at one sample of those differences. So even though it's called a paired t-test or a paired t procedure, we're really only looking at one sample of the differences. So we're going to proceed to use one sample t procedures. All right. Now, to compare a paired t-interval, we are still going to use our panic model, and we're still going to do our state plan do conclude. So remember, the state is in the parameter, and here we now are trying to estimate mu d, the true population mean difference of insert here. In our plan step, we'll check our assumptions, and we'll name the interval. And again, we have randomness, either random assignment or random sampling. We'll check the 10% condition to ensure independence within the sample. And now our pairs, since we're doing these 2 pairs, right, or the 2 differences, the difference of the 2, we want independence between our pairs. And I don't want my pair data to influence your pair data. So we're also going to check independence between the pairs. And then we're going to check the normal condition such that the sampling distribution of the statistic is approximately normal. And we can do this again by being told that the population of the differences is normal, by having at least 30 observations in our sample, or we have a graphical display that reveals no extreme skewness or outliers such that it's approximately symmetric. Now, our statistic here is going to be x bar d, and I don't know why, but this should be up here, not down here. So we're doing this based on this assumption, x bar d closely estimates mu d. Now, if these conditions are met, we will use a matched pairs t-interval for a mean difference, or you can just say a paired t-interval for mu d. We're still going to have our degrees of freedom, n-1, and we'll still use this formula here. So you will need your formula sheet handy so we can find this critical value. And notice here that the subscript, the xd and the sd, this is because we're looking at the differences. So this is the average of the differences, this is the standard deviation of the differences, and we'll still represent our sample size. And of course, the interpretation has not changed. We are C% confident that the interval from blank to blank captures the true population mean difference of yada yada. All right, so let's take a look at an example here. So here's our prompt. So here we're investigating the age of the maternal grandparents of students. So I have 10 separate students here, and I'm looking at the differences in the age because we all know age is just a number. So we're going to look at the true mean difference of the ages between the grandmother and the grandfather. So you'll notice that here, even though it's one student, student A, their mom's mom is 75 and their mom's dad is 74. So we take the difference. So you'll notice that the mean and standard deviation are calculated for both different samples, right? Here's the grandmother, again, of the same 10 students. Here's the age of the grandfather, also the same 10 students, and they have these two different values. But what we're interested in is the differences. So these two statistics are computed by this one sample of the differences. Now, notice that the means, they don't have to be independent in order for us to add or subtract. But the standard deviations, if I were to use the Pythagorean theorem of statistics, these two would not give me 5.81. This 5.81, again, is based on the sample of the differences here. Okay, so we look and we plot our distribution of the differences as we see here. And on the AP exam, you may be expected to plot them to show how the normality condition is met. But because I'm nice, I will go ahead and give you these plots. And a dot plot is best for this because it's small data and we can easily see if there's any extreme skewness or outliers. And just by investigating this, it doesn't look like we have too much to worry about. Well, I'm asked to construct and interpret a 95% confidence interval for the population mean difference. So I will start by stating that I want to estimate mu d, the true mean difference in age of maternal grandparents of high school students with 95% confidence. In my plan step, I was told that I had 10 students. I had an average difference of negative 1.8 and a standard deviation of the differences of 5.81. I'll check my conditions and I have a random sample of 10 high school students, so I can generalize to the population there. It's reasonable to assume there's at least 100 high school students in the population. It's also reasonable to assume my grandparents' age won't influence your grandparents' age since we're two separate individuals. So my data, my pairs won't influence your pairs. And lastly, the normal model seems to be appropriate since our sample data appears approximately symmetric. Since my conditions are met, I will use a one-paired or a paired t-interval for a population mean difference, or just a paired t-interval for mu d. Next up, I'll calculate my degrees of freedom, and I do that by doing n minus 1 to give me 9. And I have 9 degrees of freedom, and I'm using 95% confidence, so I'll go here to my t-table. Here is 95% confidence. Right here is my confidence level, and I'm going for 9 degrees of freedom, and that looks like this critical value here of 2.262. So what's going to happen is I will use that critical value in my calculations right here. I've got my average difference, standard deviation of the differences, all of this. I find my standard error. Standard error times critical value gives me my margin of error. And then from there, I compute the interval between negative 5.956 up to 2.356 years. Because again, these are averages, these are means. These numbers have units. And in conclusion, I'm about 95% confident the interval from negative 5.956 years to 2.356 years will capture the true mean difference in age of the maternal grandparents of these high school students. Now, this is a crowd favorite on the AP exam. Based on the interval, is there evidence of a mean difference between the ages of the grandparents of the students? Well, if there's a difference, that means we are different from 0, right? If the interval is completely positive, that would mean, if we look at how our data is defined, if the interval is completely positive, that would mean the grandmother tends to be older than the grandfather. Or if the difference is completely negative, that would mean that the grandmother tends to be younger than the grandfather. But if 0 is included within our interval, the only way 0 can be included is if there is actually no difference. And I look here, and it does appear that since 0 is here, I might not have a difference. So we are going to say something like, since 0 years is within the 95% confidence intervals, we do not have evidence of a mean difference between the ages of grandparents. It's actually quite likely that they might end up being the same age. So based on this interval, I don't have evidence that one grandparent tends to be older than the other. So that's just kind of a summary there on a paired t-interval for a population mean difference. So again, even though I am taking two separate data points, one of the grandmother, one of the grandfather, the statistics that I'm looking at specifically are right here about the differences. So once I compute those differences, I find out these two values. Okay, So let's take a look here at another example. So I'm going to leave this here for you. Go ahead and pause the video and look over the prompt and give yourself about 5 to 7 minutes and we'll come back together to review the answers. Okay, so we look here at our regular versus genetically modified corn, and fun fact, this question was our practice question when the coronavirus had first started back in 2020, so I'm quite fond of this question. And we look here, and it appears that the confidence interval is given from 2.636 to 6.436 bushels per acre. Based on this interval, is there evidence that one type of seed produces a higher yield than the other? Well, yes, because 0 is not in the confidence interval. Yes, 0 is in our data, but it's not in the interval. It's not in the estimate of the true population mean difference. So I noticed that that means genetically modified minus regular must be greater than 0, which means on average, the genetically modified seed has a higher yield than the regular seed. And so I would just phrase something like, yes, there is evidence, and this is because the interval is completely positive. So if you have a completely positive or a completely negative interval, that's indicative that there is a difference. One of those values is greater than the other. Now, based on our results, because it is mostly positive, we see that actually, it's not mostly, it's completely positive. We see that the genetically modified corn produces a higher yield. So when 0 is in the interval, we do not have evidence of a difference, but when it is not in the interval, we do have evidence of a difference. If I were asked to describe the distribution, we're looking at the cusp here. And center would be a median, and look, our statistics are already here for us. I have a median of about 3 bushels per acre. I've got an IQR of about 6.9 bushels per acre, one outlier here at approximately 20.1 bushels per acre, and my shape would appear skewed right. So I've got a cute little description here for you. And now my favorite question is, why can the normal model still be used despite the skewness and outlier in the distribution? Well, remember, our normality condition isn't about the distribution of the sample. It's about our sampling distribution. Well, we weren't told that our population of differences is normal, so I checked the CLT as my next condition. Well, I look here, 33 is larger than 30, so the central limit theorem applies, and now the sampling distribution of the average difference is approximately normal due to the large sample size. So even though I do have some skewness and an outlier in my sample display, that is outweighed by the fact that the central limit theorem will guarantee that our sampling distribution is going to be approximately normal. So like I said, on the AP exam, they love asking the classic what if question. So while most of the time our conditions are going to be met, what do we do if they're not met? Why do we have these conditions? How can we ensure normality? Why is it important that they're independent? Things like this. So hope you learned a little bit more about paired T intervals. In the next lesson, we're going to focus on running a hypothesis test for a mean difference. So stay tuned.